All right, today we're going to talk about different number types and properties of real numbers. So when you first start learning numbers, if my kids were going to learn numbers, you start counting with ones. You go 1, 2, 3. That's a list of natural or counting numbers. So 1, 2, 3, 4, 5, 6, 7, and so on. 1, 2, 3, and so on. Those have a symbol of n for natural numbers. We're going to put that on the inside. These are all natural numbers. This is 1, 2, 3, and so on. Whole numbers, on the other hand, you get a little bit older, you start introducing the concept of zero. So whole numbers start at 0. They include all the other counting numbers, but they also include 0. And whole numbers have a symbol of W. So I'm going to put W right here, and the only one that's already not included in that rectangle below is 0. So it also includes 1, 2, 3, obviously, but that's already included in the inside rectangle. Integers are positive or negative whole numbers, meaning we can have any negative number, and we'll say negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. Those would all be integers. Integers are not I. Integers instead are Z. I'm going to put Z up here. That's the symbol for integers, and so we'll add negative 3, negative 2, negative 1, and all the negative numbers to this diagram. Last one in this left half is rational numbers. Rational means you can write it as a fraction. And we can write this as P over Q, meaning if it can be written as a fraction, typically what happens with that, either it terminates or it repeats. And we'll give you a couple examples of that. So maybe something like 2/3. That can be written as a fraction. Or 0.32. And that terminates, meaning it doesn't go on forever. 2/3, on the other hand, if we wrote that as a decimal, it would be 0.6 repeating. And it repeats over and over and over again. So this one on the left repeats. The one on the right terminates because it stops. There are no other decimal places after the 3-2. These are rational numbers, and they have a symbol of Q. So we'll add Q up here. We'll give a couple examples just like we did. We said 2/3, maybe negative 0.6 repeating. Those are all examples of rational numbers. And again, if it can be written as a fraction, it is a rational number. All right, irrational numbers. The most famous one probably is pi. An irrational is a non-terminating and it's also non-repeating. So it goes on forever, but it doesn't repeat itself. Another example of something like this that you're familiar with would be something like √2. If you type it into a calculator and get a decimal value, it goes on forever, but it does not repeat itself, much like pi. So these are irrational numbers. Symbol for irrational is I. And we're going to put those on the right side over here. These are all irrational, like pi, √5, and I'll give you another example, something like 3.12122, 1222, and that pattern is going to repeat itself. Well, while that does repeat, it does not act like a stamp where it repeats itself over and over. The pattern will continue though. So that is a little bit different than something that actually repeats itself over and over and over again. So every one of these up here, that whole chart up there, these are all real numbers. And they're usually categorized as either rational or irrational. and the symbol is an R. So all of these numbers, everything in this box up here, all of those are real numbers. So on your test, you're going to get a question like this that says classify this in as many ways as possible, and we're going to use the letters here. So the number 56, and we'll start from the top. Is it a natural number? Yeah, you can count to 56. So I'm going to say N for natural number. It's definitely a whole number. It's also an integer. And it is a rational number. We can write it as a fraction. Again, if you're in doubt, 56 over 1 can be written as a fraction. And this is also a real number. And all of these are going to be real numbers, so this should always be the first one that you write on your test. Go ahead and pause the video right here, see if you can do the next three, and see if you can classify these in as many ways as possible. All right, 5.6, that is not a natural number, it's not a whole number. It is not an integer, but it can be written as a fraction, so it is a rational number, and all of these are all real numbers. 5.6 repeating, a little bit different. Okay, it does repeat. Remember what we said, when it does repeat, that is a rational number as well, and all of these are real numbers. This next one, it looks like repeats, but it's a pattern. And it looks like it goes on forever and ever and ever. This is a irrational number over here, which is also a real one. All right, next one, it says graph all of these on a number line. Let's see if we can sketch a number line. And we'll put in 0, all the way 1, 2, 3, 4, 6, 7, 8. We'll go all the way to -3. All right, -1 first off, and I'm going to draw these all above the number line so we can see them a little bit better. -1, we'll put a circle right there and label it as -1. Root 19, I'm trying to think about what two whole numbers that is between. If you're in doubt, think about perfect squares. Root 16 and root 25. Root 16 is 4. Root 25 is 5. So we know that it's somewhere between 4 and 5, probably a little bit closer to 4. So I'm going to put that over here and say that this is root 19. 2.8 is a little bit closer to 3 than 2. And -2.5 is halfway between -2 and -3. Down here. All right, this next piece is a little bit harder than meets the eye for some people. It says compare the two numbers, use greater than or less than. And always remember, if you're putting these in, it eats the bigger number. What you want to think about is if we put these on a number line, which one would be on the left, which one would be on the right. If I'm going to put this first group here, I'm going to say that this is -1 and this is -2. -2 is over here, and -√2 is about -1.4. So this is -√2, this is -2 over here. So which one is greater is always the one that's to the right on the number line. So I'm going to say that -√2 is greater because it's further to the right on the number line than -2. Go ahead and go ahead and pause this video and see if you can complete these last three. All right, this first one, when I'm thinking about 4 versus root 17, this is root 16 versus root 17. Clearly, root 17 is bigger than root 16. Obviously, root 16 is the same as 4. Root 29 and 5, I'm comparing root 25 to root 29. 29 is bigger than 25. And lastly, over here, root 50, you got to think about what that is. I know that root 49 is 7. So root 50 has to be bigger than 6.8.